These are the short notes on how to do Bohr models. So for the Bohr model, what we're going to do is we're first going to identify how many protons, how many neutrons, and how many electrons that it has. And then we're going to write the electron configuration that's going to help us with figuring out how many electrons are going to be in each shell. So then what we're going to do is look at putting in our protons and our neutrons and pretend like that's the center of our atom. And then I'm okay if you draw half shells. You don't need to draw full circles. So then the first thing I'm going to do is draw my first energy shell, because I know I have my first energy shell. And then I'm going to look at saying, okay, there's 2 electrons in that first energy shell. So those two things go together. So we're going to use our electron configuration to help us figure out how many electrons are in each energy level. So the next thing I do is I know I've got energy level number 2, or energy shell number 2. And so I look at here and I've got 6 plus 2 is 8. So I have 8 total electrons in the next energy shell, and those two correspond. The last thing I'm going to look at is I've got one more energy shell, so I'm going to draw the next half moon looking diagram here, and I'm going to add up 4 and 2, and I know that that's 6, so I have 6 electrons there. So I know I also have 6 electrons in my outer energy level. So when we talk about Bohr models, we're going to talk about valence electrons a lot, and valence electrons again are located in an atom's outermost energy level, so we call that N, and we call it the valence shell. And these are the most important electrons because they're the ones involved in bonds. So the number of the electrons in the valence shell is the total number in the S and P subshells of that shell. When we put together orbital diagrams and valence electrons and electron configuration, it will look something like this, and we're going to look at identifying the valence shell. So the valence shell has the highest number of electrons in it. It's the highest number of shells, having the electrons in it. So we've got, if we're looking at carbon, 1s2, 2s2, 2p4, 2p2, so our electron configuration would be that, and I would look at, I know that I have 4 electrons in my outer shell because it's the electrons in the s orbital and in the p orbital. Same thing with silicon. I know that I've got my 3 is my outermost energy shell, and I have 4 electrons in that. I have 1, 2, 3, 4. So again, the S and P subshell go into making what goes into your outermost energy shell. So push pause and please identify the following electron configurations and circle the valence shells in each of those. Hopefully you pushed pause and you were able to identify them. So in chlorine, 3 is my outermost energy shell, and I have 7 valence electrons. In argon, 3 is my outermost energy shell, and I have 8 valence electrons. Potassium, 4 is my outermost energy shell, and I have 1 valence electron. Calcium, 4 is my outermost energy shell, and I have 2 valence electrons. And then scandium, this is a trick question, remember from when we were learning about electron configuration. Just because it's the last thing in my electron configuration does not mean that it is necessarily the outermost energy shell. So 4 in this case would be my outermost energy shell, and it has 2 electrons. So my D block metals have a varying number of electrons in the outermost shell. So valence electrons and being happy. So atoms want to have their last s and p orbitals full. So to have that, we call it an octet. So s has 2 electrons, p has 6, so 2 plus 6 is 8, so that equals an octet. Noble gases are all happy as they have full octets. So every atom wants to gain or lose electrons to be most like a noble gas. Our only exception is helium, and it has 2 electrons because it only has 1 shell, and that first shell can only hold 2 electrons. So again, everyone wants to be like a noble gas, so they will gain or lose electrons in order to do so. So our last thing that we want to talk about is just Hund's rule. So the desire to have unpaired electrons counts for the fact that the transition elements s electrons get swiped to complete the d subshell and make it a half subshell instead of 4s being full and 3d being almost full. And so things will move, things are happy, atoms are happy when their subshells are all the way full, all the way empty, or half full. And we'll build on this knowledge way more in the periodic trend unit.